All right, so in this latest video, we're going to add a little bit to our plan for factoring. And it's going to be a welcome addition because we've seen how tough it is to factor those trinomials that have a number in front of x squared. And what we're going to see is that there's a certain way out of that sometimes, but we have to be on our toes. So our goal here is to use knowledge of special products to help with factoring. So first, we're going to remember back a little bit from when we were doing multiplication. We saw some things that were called special products when we multiplied polynomials. We were doing a whole lot of FOIL work. We were doing a whole lot of binomial times binomial distribution. And we just kind of took some time at the end and said, hey, look at these patterns that are developing in the answers. Let's just make a note of that for future. Well, now it's the future. So one thing we saw was the product of a sum and a difference. And that would be something along these lines. So it's that symmetry we're used to seeing with an x term and a constant in each of two sets of parentheses. But then there's really some symmetry here because the same players, the 3x and the 2, appear in both, one being a positive and one being a negative 2. And what we saw was that when you FOILed this thing out, or multiplied this thing out, we got our 4 terms we're used to seeing. But because of that symmetry, these 2 middle terms were opposites, and they canceled by the time we simplified at the end. And we called that end answer a difference of squares. Well, now that we're in the world of factoring, we're going to look at something and recognize it as a difference of squares and notice that we're going to be able to factor it as a product of a sum and a difference. So how are we going to notice when something's a difference of squares? Well, one thing that stands out to me is it has 2 terms. We've been spending a lot of time doing 3-term factoring, and really the only 2-term factoring we've done so far has been GCF. And if you look at the 9x squared and the 4, there is no greatest common factor. But here's some things about those 2 terms. They're both perfect squares. The 9x squared looks every bit like you took 3x and multiplied by itself. The 9 is a perfect square. The x squared is a perfect square. So that's a perfect square. And then the 4 is definitely a perfect square also because that's 2 squared. And then there's a minus sign in the middle, a subtraction between the terms. So if we were to see something like that, we would identify it as a difference of squares, and we would think if this is going to factor, it's going to factor a lot like this over here. 2 sets of parentheses, 2 terms in each, everything split perfectly even with 1 plus and 1 minus. We also saw a different special product when we were multiplying. We saw squaring 2 terms. And there was kind of a big deal made about how when you square 2 terms, you do not just distribute the exponent. Exponents do not distribute over subtraction. What we learned was that you really need to think about it as 2 copies of 5x minus 3 multiplied by themselves. So that would lead to FOIL, and that would lead to 3 terms because our outer term and our inner term are both going to be 15x's, negative 15x's for that matter, and you put them together and get a negative 30x. So the middle term didn't disappear like up here. You kind of piled them up. But there was a lot of symmetry there also. So this middle term had a connection, and there's a lot of connections here. What we said at the time was, hey, if you look back, this thing here is going to be called a perfect squared trinomial. And if we look back, we're going to be able to see 2 things that were in the original problem, a 5x and a 3. We call one A, we call the other one B. And when you start looking at the answer, the 3 terms down there, you're going to see some reflection. You're going to see it looks like you squared the 5x. It looks like you squared the 3. Call it B squared. But then there's this middle term here that is the outer plus the inner, but it's also the outer twice. Because of all the symmetry, the inner and the outer are the same, so we called this thing 2AB at the time. And it was just kind of a, okay, well, nice to know. I'm not going to use that very often. I usually just FOIL here. But now if you're trying to work this backwards, think about what this does for us. We've seen how hard it is to factor a trinomial that has a number in front of x squared, let alone a number as big as 25. If we have to start guessing the checking or think about this like observation of outer products, we're going to have our hands full there. But if we could go into this ahead of time and say, you know, certain trinomials are perfect square trinomials. They have 3 terms, like every trinomial does. The first and third terms are perfect squares. This makes me think that someone squared 5x. This makes me think that someone squared 3. They're both perfect squares. And then that middle term has the right connections to the 5 and the 3. This is 2 times 5 times 3. 2 times 5 is 10, times 3 is 30. If that middle term is 2AB, then you have a perfect square trinomial. So how's this going to look then? Let's get back to factoring. For today, the directions are going to say, factor this kind of problem. So it's going to be a signal, hey, this is the difference of squares. But eventually those directions go away and it'll just say factor. And what you should be thinking is, with two terms, I should always look for a GCF. And I see 4s and 2s and D's and 8s. But I only see 9s and 3s and 81s. I don't see a common factor there, so there's no common factor. But I do notice that they're both perfect squares. It looks like someone squared 4D for the first term and someone squared 9 for the next term. And if that's the case, if this is a difference of squares, then the factored form is going to look like this from the earlier conversation. Two sets of parentheses, two binomials, perfectly split. A squared gets split, B squared gets split, and I'll get 1 plus and 1 minus. So in this problem, if A squared is 16D squared, and B squared is 81, we can then figure that A, when we go to fill in this formula for the factored form, A should be 4D, and B should be 9, and the signs are built into this. So we'll get 1 plus and 1 minus. My 4Ds go there, my 9s go there, I'm factored. Certainly not a GCF. Probably not quite the reversing FOIL, what two numbers multiply to. It's more of a standalone special product where you say, if both of these are perfect squares, there's something we can do for that. On this one here, you could guess and check on this thing. And you could use that kind of outer product, what two numbers multiply to and add to. But there's some pretty big numbers. And that guessing and checking would be a handful. I would recommend that when you see a three-term problem, whether it says this is a perfect square trinomial like the directions will today or not, you go, I wonder if this first guy is a perfect square. That makes me think of 2x. And I wonder if this last guy is a perfect square. That makes me think of 11. And if this middle guy is 2 times 11 doubled, 22 doubled it is, then this is a perfect square trinomial. So that's the expression we were given. In this case, the 4x squared is a squared, and the 121 is b squared. So it makes me think that, as I said earlier, a is 2x and b is 11. That middle term checks out. So that means my factored form is going to look like that. Or that, however you want to describe it. But we certainly know that when you have, this is a perfect square, and this is a perfect square, and this is 2 times a times b in the middle, we know that there's going to be perfect symmetry between this set of parentheses and this set of parentheses. So whether you want to write it as 2 sets that match perfectly, or you want to write it as 1 set squared, that's fine by me. Either one's good. So you could write this as 2x plus 11 times 2x plus 11, or you could write it as 2x plus 11 squared. So that's going to be today's work then, is we're going to give you a title and say, hey, here's the kind of problem we want you to do. And then you can probably imagine that very shortly we'll stop giving you the directions, we'll give them mixed and say, well, why don't you just put your plan to practice. But there'll be one more video summarizing the plan before you do that.